Okay, this is part two of chapter 12, analysis of variance. And this will concretize it somewhat. We'll go through that example, do some hypothesis testing, and finish off the conceptual parts. Okay, so when we calculate the F ratio, we're going to be filling in this ANOVA table. This is called the ANOVA source table, and it is what we're going to be using in step 3 of hypothesis testing. So up top there, you see all of the different symbols and notations for the statistics. When we fill it in the bottom, I'm going to be giving you the sums of squares between and the sums of squares of within. This is the part of the textbook they talk about getting it from raw data. We're not going to do that. We're a little short on time with this semester. And I want you to understand it conceptually more than kind of at that level of raw data. So I'm going to give you the sums of squares within, the sums of squares between. From there, from the situations, you'll be able to calculate the degrees of freedom as we've talked about already in the last show. And then once you have the sums of squares and the degrees of freedom, you can combine them to get the mean squares in each case. Take the sums of squares of each and divide by the degrees of freedom of each. And you see there had been a typo, but I just fixed it, right? These are now W's. Once you get the mean squares, then you can calculate the F ratio, the F statistic, by dividing the mean square between by the mean square within. So this is effectively going to be the step 3 of hypothesis testing. But let's back up before we get too far into the numbers. Let's take this memory experiment example forward, and we'll start with the hypotheses. As always, the hypothesis is that there's no difference. So the base hypothesis in this experiment, any ANOVA, is there's no difference between the samples of behavior. In this case, we've got 3 memory strategies, and we're asking, does learning strategy affect memory? And just so you remember, K was 3. There were 3 strategies: rote rehearsal, imagery rehearsal, and sentence creation. And there were 45 people in that entire experiment spread among those 3 groups. So according to the null hypothesis, there's no difference between the 3 memory strategies. So what does that look like? Well, if there's no difference, the null hypothesis is that the population mean for each theoretical population represented by the samples is not different. So mu rote equals mu I imagery equals mu sentence. There's no difference between those populations. If there is a difference, then we put a does not equal sign between them. So the alternative hypothesis is that mu rote does not equal mu imagery, does not equal mu sentence. These are always going to be the hypotheses for analysis of variance. We represent each population here that is embodied by a sample in the experiment, and we think about the relationships between them. The null hypothesis says there's no difference between the populations. The alternative says there's some difference. And to remember this, think back to Sesame Street. Really what this alternative hypothesis is saying is at least one of these things is not like the others. Now this is where analysis of variance is an omnibus test. It only tells us something is going on. It doesn't tell us exactly what that is. So it says one of these things is not like the others, but doesn't tell us which one it is, and it doesn't tell us if that population is higher or lower than the rest. The second step of hypothesis testing is setting up the rejection region. The F distribution, here's a chart showing some F distributions. This is like the T. There's a different curve for every different degree of freedom, and the red one is showing for 1 degree of freedom, 1 DF between and within. And then see these are just numbered 1s and 2s. There's a different curve for each situation depending upon N and K. But what they all have in common is that they are skewed. right? They have this shape where they're kind of humped up near the y-axis, and then they run out long on the x-axis. The ANOVA, the F distribution is a one-tailed distribution. There are no negative scores with F ratios. And that makes sense. Remember, we're dealing with variances, and variances are always positive. We take the squared deviations, right, and we get the deviations, square them, and then average them. So when we square those deviations, anything negative becomes positive. You could think of this as a t distribution folded over on itself, right? So if you had a t distribution on a piece of paper, increased it at 0, and folded the left half, the negative half, onto the positive half, that would be the F distribution. And we can do that because, remember, we're squaring. Anything that would be negative is squared, becomes positive, so it folds over. So this is a different kind of distribution than we're used to seeing. It's effectively a one-tailed distribution, and you see where the one tail comes from in a bit. Now be careful, right? The alternative hypothesis was does not equal. This really is a two-tailed test, but in function, it only has one tail. And as you see, we need 2 degrees of freedom to figure out where the level of significance falls on this chart. So to use, to understand the rejection region, we need to find both degrees of freedom between and degrees of freedom within. And in this chart, they're labeled 1 and 2, and that's often how they're labeled in tables as 1 and 2. 1 is always the numerator, degrees of freedom, which for us will be degrees of freedom between. 2 is the denominator, degrees of freedom, which is DFW. Of course, as a rejection region, we also need to know the level of significance. So to find the critical region, the critical value of F, we need 3 things: DF1, DF2, and the level of significance. We're going to be using a new table. It's the F table, and there's one in the appendices of Top Hat. I've also pasted one in Blackboard. They're slightly different in function, but we'll go over them, and they make sense. The way they work is in Top Hat, there is 2 separate tables, one for 0.05 level of significance and the other one for 0.01. And here you see a snapshot of it. And the green column headers is 1 degrees of freedom, and the brown column headers here, the darker column headers here, are the other degrees of freedom. Unfortunately, they're not labeled in the Top Hat table. But it's, remember, degrees of freedom 1 is going to be the columns, usually always the columns in a table. So all of those are degrees of freedom between. Right? Remember, degrees of freedom between is K minus 1. Degrees of freedom within are represented on each row in the green, the green row headers there. And degrees of freedom within are N minus K. Right? So to use this table, you would find the conjunction of the 2 degrees of freedom, and that would be the critical value. So the critical value for, as we say, here's the typical way to do it. Say we have F for 3, and 6 degrees of freedom, right? It's always degrees of freedom 1, degrees of freedom 2, right? Degrees of freedom between, degrees of freedom within. So we would need the conjunction of degrees of freedom 3 and 6, which is that one right there. So the critical value would be, in that case, 4.76. The table that I put into Blackboard is slightly different. It has, though, degrees of freedom between and degrees of freedom within represented in the same place. I like this one a little bit better for 2 reasons. One, right, it says numerator degrees of freedom, and you should know, right, that refers to the F ratio. So degrees of freedom between are the columns, degrees of freedom within, denominator, are the rows. This one has 0.05 and 0.01 in the same table. So in this case, 0.05 is light face, 0.01 is bold face. And it's a little bit hard to see, but you can make it out. They always put the light face type on top. So if we look at the conjunction, let's just say 5 and 3 degrees of freedom. Here's the conjunction for 5 and 3 degrees of freedom, and there's two values. The top one, light face, is for 0.05. The bottom one, in bold face, is for 0.01. You can use either table, you'll get the same critical values. So to set up the rejection region for analysis of variance, remember we need the 2 degrees of freedom and we need the level of significance. So let's make alpha 0.05 for this. And for this particular test, the memory study test, K was 3 and N was 45. So the degrees of freedom between is 2 and the degrees of freedom within is 42. So this is from the table that is in Blackboard, right? So this would be right here, this column is this 2 degrees of freedom between, and we go down, it's on the second page, really 42 degrees of freedom within. There's the two possible values. 0.05 is the light face, 3.22 on top. 5.15 would be for alpha 0.01. So the critical value for the test of in the memory studies is going to be 3.22. Now here's this is from the top of the chart and of this chart, and I think this is a good way. I like to think of rejection regions in terms of pictures. This is an F distribution, right? Here's right. This represents F values for 2 and 42 degrees of freedom. Right, there's the chart. The critical value marks off the level of significance, so the shaded area represents that proportion, 0.05, and the value is that particular F score that marks it off. The rejection region is always, see how it's shaded? It's always greater than the critical value. There's no negative F values, right? It looks like a one-tailed rejection region, but remember the alternative. It's really two-tailed. So here we're going to reject the null hypothesis if the F observed is greater than or equal to, and it's always going to be greater than or equal to the tabled value here, 3.22. All right, there it is. We're going to reject the null hypothesis if the F we observe is greater than or equal to 3.22. Always going to be greater than or equal to. What will change will be the critical value, which will change given the particular N and K for that problem. But this rejection region, if you're going to draw it, always going to be a skewed distribution. The F distribution is not a normal distribution or a near normal distribution as the T is. It is a skewed distribution. So get in the habit of doing this, kind of making a chart like this that looks very skewed, and you'll be okay. All right, so step 3 then is filling in the table. And you see here in red, I've provided the sums of squares between and the sums of squares within. So now we just need to fill in the rest of the table to come up with the F ratio. We've already found the degrees of freedom, right? We needed them for step 2, the critical, to find the critical value of F. So in this case, they're 2 and 42. Remember, right, degrees of freedom between, here it is up here, K minus 1 gives us 2. Degrees of freedom within, N minus K, 45 minus 3 is 42. So there I have the sums of squares and degrees of freedom. Now I can move on to the next step, which is finding the mean squares. So for each row, I divide the sums of squares by the degrees of freedom to get the mean squares. So the mean square between equals 8530.75. How to get that? 17061.5 divided by 2. And there's the answer. Same thing down here with the mean square within. Sums of squares divided by degrees of freedom gives me the mean square. Traditionally, ANOVA tables are written in this way between over within, between row over the within row, because that's how the F ratio works. The F ratio is a mean square between divided by mean square within. So when we do that division, 8530.75 divided by 316.56, we get 26.95. Sorry, I'm seeing a typo here. It happened again. I missed that one. Those should be W's, right? But the F ratio is 26.95, right? This is always going to be blank. In this case, a one-way analysis of variance, we only have one F ratio. So this cell is always going to be blank. There's our source table for ANOVA. It's got the sums of squares, degrees of freedom, mean squares, and the F. I'm going to give you guys this stuff. All of this comes, the rest comes from the problem. Get degrees of freedom from the problem, and then we can find the mean squares. Step 4 is making a decision and stating the conclusion. So, the rejection region, right, there's my skewed distribution, the F distribution, showing the rejection region marked off by the critical F for alpha 0.05, and our particular 2 and 42 degrees of freedom, that critical value is 3.22. So we're going to reject the null hypothesis if the F we observe is greater than or equal to 3.22. In this case it is, right? The F observed was 26.95. So hopefully you see where this is headed, right? It's way, whoop, there it is, way out here. So we're going to reject the null hypothesis, and the conclusion is that we have evidence that at least one of the memory strategies differs from the others. This is as far as we can take the conclusion with analysis of variance. Remember, it's omnibus test. It only tells us if something is different. We can't get any more specific right here. Now, this goes against what we did with the z-test and the t-test, right? If we had a two-tailed alternative hypothesis, in the end, we make a statement that sounds one-tailed, right? And this was on the exam, and it's been the case with the t-test we've been doing. If you are just looking for a difference, the null hypothesis is two-tailed. You don't know at the start. But after you do the study, you know which mean is higher or lower than the other. We know which group scored better or scored worse, and we should say that with a t-test. But with analysis of variance, we can't. Analysis of variance, all it tells us is something is going on. At least one of those groups is different from the others. There are ways in which we can determine it, but that is beyond the basic analysis of variance. Those involve what we call post hoc tests, after the fact tests. And there are actually different versions, different kinds of t-test. But if we reject the null hypothesis with analysis of variance, excuse me, we would be obligated to dig further to see what the differences are. We're going to save that for your next stats course, and that might be in methods where you talk about post-hoc tests. That would be appropriate, but we're not going to go there at this point. Just leave it at, right, if you reject the null hypothesis with analysis of variance, you probably are going to need to do further digging to see exactly what's going on. As a good researcher, you're not going to stop with this. You're not going to let the world have your conclusion to the world be, yep, we know one of these memory strategies is different, but I'm not going to tell you. You would find out how they're different and which one is the best. But that's the next step that we're not going to do. Now let me just play a what if. What if we failed to reject the null hypothesis here, right? What if we got something that was over here, right? An F ratio less than 3.22. Well, something over here would be we would fail to reject the null hypothesis, and the conclusion would read the same except for the word no right there. If we fail to reject the null hypothesis, then we have no evidence that the memory strategies differ from each other. The stuff that we talked about with logical errors, type 1 and type 2 errors, apply here as well. If we reject a null hypothesis, we've run the risk of a type 1 error. If we fail to reject, we've run the risk of a type 2 error. Right? Those are errors tied to hypothesis testing, not particular procedures. So those would apply. There are also ways to determine effect size in analysis of variance. It's discussed in the chapter, but we're not going to get into it. We're going to leave that for your next class. Can't do everything in one class. A good comedian once said, always leave them wanting more. So with that, this will be the end of the lectures for stats.